In this video, we're going to introduce sort of an abstract concept of state functions, but we're going to show why these state functions can be useful in helping us to understand better the energy changes that occur in reactions. So our learning goals include the nature and utility of state functions, and we're going to see how they get employed in learning new things about chemical reactions. Now we'll start off with a little bit of a fun exercise. Let's consider the Sombria in the center of the UTSA campus, and I would ask the question, which is higher, the Sombria or the top of the Empire State Building? Now, this is something that you really can't compare directly because they're thousands of miles apart. So we're going to have to evaluate them relative to a standard, and in particular the standard that we typically use for this purpose is sea level. Now, if I did a little bit of internet research, I would find that the Empire State Building is 442 meters tall. I can estimate that its base is about 20 meters above sea level. So how does that compare to the Sombria? Well, we don't have an altitude for the Sombria, but we know it's about the same as Helotes, and Helotes is 331 meters above sea level. So that means to go from the Sombria to the top of the Empire State Building would involve a change of altitude of about 131 meters. All right, well, what's the point of doing all of this? I mean, so what? Who cares about the Empire State Building and the Sombria? Well, it turns out that no matter what path we take, going from the Sombria to the top of the Empire State Building, if we drove a car from here to New York and rode up the elevator, or if we took a helicopter and, went all the way across the country in the helicopter, or maybe if we took a moonshot into space and then took a parachute down from there and landed on the Empire State Building, doesn't matter how we go, we'll end up with the same change of altitude between the Sombria and this Empire State Building. So it's a long way of saying that no matter what path we take, we'll gain 131 meters of altitude. And the reason that this is true is because altitude is a state function. It is a function where its change in the state function depends only on where you start and where you end. Doesn't matter what happened in between. You could have gone to the moon and come back and ridden a car across there, gone down to the bottom of the ocean, and then climbed up to the top of the Empire State Building. It still would have been the same net altitude change. All right, well, the good news is that enthalpy is also a state function. So now I want to consider the enthalpy content of 1 mole of ethane at standard temperature and pressure. All right, so we want to figure out what this is, and we are going to be measuring it relative to some standard. We're going to measure it relative to the energy or the enthalpies of its constituent elements. So by a direct path, we might say that enthalpy is the enthalpy change for this reaction of taking carbon solid, reacting with hydrogen gas to get ethane directly. There's also an indirect path we could take, though. We could say that it's from taking this set of carbon and 3 hydrogen molecules, and instead of going directly to ethane, we might make ethylene first. Ethylene is C2H4 with a hydrogen left over, and then subsequently react that hydrogen with the ethylene to get to the ethane. Now, what complication does this add? Well, the second path is actually 2 different reactions. So let's consider those separately. The first reaction is one where we take carbon as a solid, react it with hydrogen gas to get ethylene and hydrogen. And we'll say that the enthalpy change for that is delta H of sub 2A. The second reaction would be ethylene plus hydrogen going to form ethane. And that would have an enthalpy change of delta H sub 2B. So now what we want to know is what is the relationship between these enthalpy changes and the one for the direct path that's in the first equation up above, where it goes from the carbon and 3 hydrogen molecules directly to ethane. What is that relationship to reaction 1? Well, the way we're going to answer this is by looking at it as a set of energy diagrams. And so in particular, what I'm going to do is measure as a vertical coordinate the enthalpy content of the system. And we're going to start with the place where we started this particular set of processes, namely with carbon solid and 3 hydrogen molecules. So these are our reactants. Now in the direct method, the one-step reaction, we would find that we'd go down. It actually is an exothermic reaction. We go down to the enthalpy content of ethane. We would find that the enthalpy change then is negative 84.7. That gets us to our product. What if we took the other path? What happens then? Well, the first step, as it turns out, is endothermic. It takes us up to a higher enthalpy level where we would find ethylene and hydrogen. And then we would in the subsequent step, it would take us all the way down to the ethane. And it turns out we would end up at the same place. In this case, though, the first step has an enthalpy change of plus 52, and the second step has an enthalpy change of negative 136.7. So the net process is going to be the sum of those two changes. And this is in general true. And in fact, we can do it numerically. We can test that out and make sure that they do add up, and they do, to negative 84.7. So this is a great principle that we can use for enthalpy changes, and we're going to see how it works in practice using something called Hess's law in the next video.